Good evening, viewers. Glad you're tuning in with us tonight. I'm Anish Potnis, and I'm going to be your host today as we explore the methods that neuroscientists are using to look inside your head and understand how you work. If you're anything like me, you probably spend a good bit of time wondering about how things work. This guitar, for example, it's man-made. And because our society hasn't collapsed yet, that means there's at least one person on Earth who understands completely how it works.
But how would you try to understand how the brain works? Can you cut it open and try to look inside?
You can. But that won't get you very far if you're trying to understand how different parts work together, especially if there's long-range distances between them. Because of these challenges, neuroscientists have turned to advanced technology to try and help answer these questions. In particular, and only in part, they have turned to neuroimaging to help them get a look inside the head of a human subject.
Functional integration utilizes a category of methods for taking a peek inside your head to understand how different brain regions work together to create you.
Some detractors of functional integration and neuroimaging, though, they harken back to the age of phrenology, when pseudoscientists thought that by feeling the furrow of a man's brow or a bump on the back of the head, you could assess his personality composition. Detractors do have somewhat of a point. Trying to gain a wholesale picture of brain function just from external images is a bit like looking out the window without your glasses on. But despite that, I, and many other scientists in the field, believe that there are meaningful insights to be gleaned from the study of the brain through neuroimaging. First, I'm going to walk you through three major methods in the field of functional integration. These techniques are functional magnetic resonance imaging, positron emission tomography, and last but not least, magnetoencephalography. We're going to discuss how these methods work and then how they can be used to assess brain function. Let's get started.
So fMRI takes advantage of a difference in magnetism between oxygenated and deoxygenated hemoglobin. What this allows you to do is assess at different points in time what parts of the brain are taking up oxygen. While this does allow you to get a wholesale picture of brain activity, the drawback of this technique is that you can't see what individual neurons are doing, and the temporal resolution is a little laggy. In a PET scan, you first, a few hours before your study, feed your patient a tracer that contains a radioactive substance that emits positrons. What the PET scanner does is it detects the positrons. So you have a lot of flexibility in the choice of tracer as to what physiological process you want to observe. An extremely common choice is a radioactively labeled analog of glucose. And so the results of this is that analogously to how the fMRI would tell you about oxygen consumption in different parts of the brain, PET with this glucose analog will tell you about glucose metabolism in different parts of the brain. Magnetoencephalography uses highly sensitive magnetic sensors to detect ion currents in neurons throughout the brain. As you might know from your studies of physiology, ion currents are very frequently associated with the presence of action potentials, though there is always noise due to other cellular processes.
To grasp of the typical imaging modalities in use in functional integration, there's one last step we have to focus on before we actually discuss how we analyze the data we collect. And that step is understanding the difference between functional and effective connectivity. But first, let me give you an analogy.
The analogy I'm going to give you is just that the difference between functional and effective connectivity is analogous to the difference between correlation and causation. As you may be familiar from your high school statistics class, correlation does not always imply causation. If you look at this chart of the plot of the United States highway fatality rate versus the amount of lemons imported to the United States from Mexico, you see a near perfect linear correlation. But this does not imply that the lemons are preventing highway deaths. Analogously, the difference between functional and effective connectivity is that functional connectivity is mere correlation between the activity of brain regions, whereas effective connectivity is true causality, represented by the data.
Bearing in mind our correlation does not imply causation axiom, let's now move to our first mode of data analysis. This is called dynamic causal modeling, and it was first pioneered by Carl Friston approximately 30 years ago. It's a Bayesian method, and it requires some iteration and approximation on behalf of the experimenter. So the first step requires a bit of faith and uncertainty on behalf of the scientist who's doing this. What you have to do is you have to select a set of brain regions that you're interested in studying. Next, you have to propose a model of the different connectivities that could be present between these different regions. Now the problem is, starting off, you don't know what the parameters are, you don't have absolute true knowledge of what the connectivities are between these regions, but you're making a first guess that will be corrected iteratively. So you make your first guess. Then what happens is you go and with your patient, you take your fMRI or you take your MEG or you take your PET scans, and what you can do is, based on the data that you've collected, you can compute the probability that your model is correct based on the data. And then you'll end up with probability distributions for each of the connectivities between the regions that you specified, as well as probability distributions for each of the parameters that you specified. And based on that, if it strikes you as a probability of 0.001 that your parameter for one set of regions is correct, then you modify that parameter and you compare it again to the data. Statistical parametric mapping is a little bit easier to understand. It doesn't require any Bayesian modeling. What it does require is a basic elementary grasp of a student's t-test, which you should have learned back in high school.
So let me tell you what you're looking at. What I've done here is I've come up with a simplified 2D version of a data set that you might be working with when you're doing statistical parametric analysis. When you do statistical parametric analysis, your first step is to take two neuroimages of a single patient. These can be before and after conditions, change over time, change when reading a book, change when thinking about something, whatever experimental conditions you want to impose. It's very general. You then choose the appropriate statistical test for the experiment you designed. Very common choices are student t-tests or linear regression. Let's say you chose student t-test. So now, with a picture you're seeing right now, you have these two scans. On the left, you see noticeably less active, and on the right, you see noticeably more active. You go through voxel by voxel, and you compute a p-value for each voxel and assess whether it's statistically significant at your chosen alpha value. So that tells you whether each voxel exhibits a change, but you're interested in brain regions. So what you have to do yourself is compute a threshold for, okay, if this number n of continuous voxels all exhibit statistical difference, then I will consider this region of the brain to exhibit statistically significant activation over the course of these two conditions.
So the last mode of analysis is called voxel-based morphometry, and it's actually an application of statistical-based parametric mapping. So what it is intended to do is to quantify differences in brain structures both between individuals, but also between the same individual 20 years apart, for example. One typical study in which it's commonly used in is between subjects who have psychiatric disorders versus subjects who do not. And so the way this is used is it takes advantage of the fact that in fMRI, there's a noticeable and measurable intensity difference between the signals generated by gray matter of the brain versus white matter of the brain. And by taking advantage of that difference in ratios, you can estimate the proportion of a voxel that is made up of gray matter versus white matter and assess what proportion of the brain is actually undertaking functional neural computation. Thank you.